So to finish up our work on graphing, we're going to look at an application of trigonometry. We haven't looked at many at all in this class. We've spent a lot of time, many weeks, just talking about the abstract theory. So here's a nice down-to-earth application of trigonometry. And it's an example where I got this data from somebody else. It involves measuring the tides, the tidal level of the water in the Thames River in England, the river that flows through London, England. The Thames in London is very close to the ocean, so the effect of ocean tides is to raise and lower the level of the Thames River periodically from day to day. And so here we got some numbers where someone did some measurements, and at 12 a.m. at one day they measured the river depth, 27.2 feet. 1 a.m. they measured it again, 30.1, so a little deeper. 2 a.m. measured it again. And basically just have this data going over, I think this is over a 24-hour period. The measurement was made every hour. And so when you have data, you look at it and you think, gee, that's a bunch of numbers there, big deal. But one thing we learn in math is that when we plot points, we often see something we would never notice just by staring at the table of the numbers. So what we're going to do is plot these points on an xy plane where the time, the hour, is going to be the x-coordinate, and the river depth in feet is going to be the y-coordinate. And we're going to simplify things a little bit. We're going to have to do some approximating. We're just not we don't have the technical skills here to do this in a more accurate way than that, even though what we do is going to be pretty accurate. So I went ahead and I already plotted all the points, and I think you have access to this plot in Canvas, so you don't have to plot them yourselves. And what's interesting to note is that if I connect up the points that I plotted, these look like a sine wave. Sine wave or a cosine wave. Because the rising and falling of tides is what we call a periodic phenomenon that's often modeled by using a sine or a cosine function, because it's something that repeats itself over and over again through time. What I think is the most interesting thing for you guys in all of this is that we're drawing this sine wave, this graph of a trig function, or approximately the graph of a trig function that I got by connecting up the points, where the x-axis, the horizontal axis, has no angles labeled whatsoever. There's no degrees here. There's no radians here. We have time on the horizontal axis. So we're going to use a trig function to describe a situation that has nothing to do with angles at all. Any kind of periodic phenomenon, even sound waves like we saw on the very first day of class when we looked at that little sound wave app, electromagnetic radiation, all sorts of things that vary periodically can be modeled using sine and cosine functions, even though there are no angles in the situation at all. That's really where trig becomes useful, when we leave angles behind and describe these various situations that can occur in nature. So, okay, there's my little commercial, but just think about that again. No angles here. The x-axis is not degrees, not radians, but time. Yet we're still going to use a trig function to describe this situation. Now, we want to try to come up with a formula for this function. So we went from the data to a graph to a formula. A formula you can use to make predictions about the future. And we're going to have to do some approximating here to get it. We're going to apply that process that was developed or outlined on our handout, writing equations for graphs of trig functions. So the graph we're getting here for the Thames River depth is similar, the idea is similar to what we saw on this handout, because we don't have a one period portrayed, we don't have don't know whether we have to use sine or cosine. We actually could use either one. But following the model we set on this handout, I'm going to come up with a formula based on cosine, because I think it's a lot easier to set up a cosine function. So we will use cosine. And so we're going to try to identify the A, B, the C, and the D values that could be used for this graph. And so working through the steps similar to what we went through on this handout, let's think about amplitude of this wave first of all. And the amplitude is half the total height. So what I want to do is, from my data, I'm going to look for my largest y value, and the largest y value that I see is, I think, 34.4. That's the max value. The smallest y value that I see on here, I think, is going to be right there. It's 18.0 min value. Okay. So if I take 34.4 minus 18.0 and divide by 2, so take the whole total height of the wave and divide by 2, I get 8.2. That's the amplitude. That's going to be my A value that I use for the formula for this graph. Okay, so I took the highest point I see minus the lowest. Now, notice these waves don't match up exactly. So we had to make a choice. We chose the biggest y value, even though the peak of each wave does not match up exactly, right? So we are doing a certain amount of approximating. Okay. Next, we want to talk about the period. And so I want to think about the time from peak to peak, say from here to here on that graph, from 3 a.m. to 4 p.m. looks like the time span, we would say, for one cycle, for one period of this function from max point to max point. So one period goes from 3 a.m. to 4 p.m. That's actually 13 hours. So the period is 13 hours of time here. Okay, not radian measure, not degree measure, but 13 hours of time. The period is equal to 2 pi over b. So we want 13 to be equal to 2 pi over b. 13b is 2 pi, so b is 2 pi over 13. We have our b value for the formula we're going to generate here. If I follow the outline on that other handout, they looked at vertical shift next. So our graph here is not, it's actually sitting way above the horizontal axis. So we know the midline is represents a positive vertical shift, right? Upward. And here it's really difficult for me, just from the way this data is laid out, to just eyeball that midline. So I am going to rely on that formula from our other handout, where we took the average of the max value and the mid value to get the y-coordinate of the midline. So I'm actually going to take 34.4 plus 18.0 divided by 2. So I'm going to add the max to the min and divide by 2. And I get, let's see, 26.2 is, so y equals 26.2 is the midline on my graph. Y equals 26.2 is, I would say, an approximation to the midline. Here's 26.2 is just slightly above that. So roughly somewhere around there is our midline. And that means my d value is 26.2. Okay. And then what's usually the more complicated or tricky thing to compute is our phase shift. And on this graph, my phase shift is going to be how far that first max point is from the y-axis. So we know it's at 3 a.m., so we know we shifted 3 units or 3 hours to the right to get that fundamental period. So the phase shift is 3 units, which is the same as hours, to the right. I can either use the double parentheses or I can use our formula, phase shift equals C over B. Replace phase shift with 3 equals C over 2 pi over 13. And if I multiply by both sides by 2 pi over 13, I get 3 times 2 pi over 13 equals C. That's 6 pi over 13 is C. And now I'm ready to put my formula together for that function. We have y equals, A is 8.2. I'm using cosine of b 2 pi over 13 x plus, minus 6 pi over 13. Why is it minus? Because we shift to the right, so I know I'm shifting in a positive direction, sign has to be minus. Plus my d value is plus 26.2. There, sorry. And there's my formula for this mathematical model of the tides of the Thames. X is hours, y is depth in feet. Beautiful example of using trig in a situation where there are no angles, just a periodic phenomenon.